Hello everyone, hello IEEE family. We are here for our new masterclass episode. This is Emir Karaslan. I am computer engineering student in Bahçeşehir University, and I am also activity committee member in IEEE Computer Society Turkey chapter. In masterclass series, our main purpose is inform scientists, engineers, and students about recent and future technologies. Hello everyone, hello IEEE family. We are here for our new masterclass. Expand your horizon. This is Emir Karaslan. I am computer engineering student in Bahçeşehir University, and I am also activity committee member in IEEE Computer Society Turkey chapter. Professor, can you close your thank you very much. As I said, in masterclass series, our main purpose is inform scientists, engineers, and students about recent and future technologies. And we want to contribute to the science and expand your horizon. Today is a special day because, as you know, that we are in IEEE Day, and we have very valuable guest today, Professor Kathleen Kramer. Kathleen Kramer is a professor of electrical engineering at the University of San Diego, where she served as a director of engineering from 2004 to 2013. She has also been a member of technical staff at several companies, including Viasat, Hewlett-Packard, and Bell Communications Research. Author or co-author of over 90 publications. She maintains an active research agenda and has recent publications in the areas of multisensor data fusion, intelligent systems, and neural and fuzzy systems. She received the BS degree in electrical engineering, magna cum laude, with a second major in physics from Loyola Marymount University, and the MS and PhD degrees in electrical engineering from the California Institute of Technology. And now she is the 2023 IEEE President election candidate. We are so appreciated to welcome you, Professor. How are you? Sorry, can you open your mic? Thanks.
I was trying to avoid the echo. Yeah, so I'm very happy to be here and extremely happy to have this opportunity to celebrate IEEE Day.
Okay, so before your presentation, I'd like to ask some questions about IEEE and IEEE Day in order to learn your feelings about IEEE Day. So why IEEE Day is important for you?
Well, I don't know that it's the day so much as IEEE is an important part of my life, and it's an important part of the world ecosystem. I was talking to my students yesterday about it, which somehow it was not first on their mind that today would be IEEE Day. I don't know how that could happen, but it is perhaps unknown to people just the major impact that the IEEE fields of interest and those of us, and that includes the greater community that have been leading these technological developments that have completely impacted the world and advanced society. So truly advancing technology for humanity. And it all, in the end, comes back to IEEE. And so it's a great day to celebrate.
Okay, so why IEEE is important for scientists, engineers, and students?
Well, in the end, it's about bringing us together. And so there's this traditional thought of the inventor as alone in the garage, and or perhaps that's a California thought. We have a lot of garages, and so alone in the garage, and to the point where at my own university there's a special maker laboratory that's called Donald's Garage. That's named after Donald Shiley, who contributed to the artificial heart, who worked in his garage, and so the laboratory or the garage, and all by yourself. And really, it's about, there's a need to collaborate as a community, and so it's IEEE that gives us that professional community. And so there really are no, even Donald in his garage. And even I forget, I think it was David Packard that had the garage that is the founder of Silicon Valley. So and Thomas Edison in his workshop, there was no working alone going on in there. There were some great inventions kind of alone, but they didn't change the world until there was collaboration.
Okay, so my last question is about IEEE and IEEE Turkey. What do you think about the studies of IEEE Computer Society Turkey chapter, and what suggestions you can give for us to improve our studies?
Give me that question, I'm sorry, one more time.
Okay, what do you think about the studies of IEEE Computer Society Turkey chapter, and what suggestions you can give for us to improve our studies?
So are you so where should I direct you to improve? How should you improve your study? Like, what advice should I give you? Is that what you're asking?
Yeah, definitely. Yeah.
Oh, okay. So I'm going to I'll give you a little bit, and then I want you to save that and ask me that same question at the end of my talk.
Okay, sure.
And so so before you hear my talk, I think there's the important point is to have a love of learning. And for me, there was a major leveling up that occurred between my high school and my college years, and then my college years and my graduate studies. And it was when you were in high school, at least in my experience, you need to get serious, and you need to get to work, and you need to do what you're supposed to do to move forward. And then to succeed as an undergraduate, you're looking to learn, but it's a very difficult lesson to get to the graduate school ready level, where the point is the impact of your work rather than getting an A or getting the high mark. And this takes, it's not just maturity, but a professional awareness that has to develop. And I would also just give some offhand advice that, you know, the world is full of people who are really your friends and want to be your friends and want to help you. And if you are a person that they see as want to help them. And so I personally like my time is valuable, but my time is spent with you right now. In the end, I want every single person that's listening that they're a little better off because they attended this webinar. And I would love for students to think of that, you know, your time is valuable and other people's time is valuable. Make it more valuable because you were there. And so be looking for that opportunity. And so you could look at it as, oh, I'm going to get an A if I do this, or I'm going to make more, I'll get a raise if I do that. And I honestly never look at it that way at all. I'm very energized by the opportunity. So you and I have just met right now. I hope that I haven't forgotten meeting you in person. But in the end, from now on, for the rest of our lives, we'll run into each other and we'll have this in common, and we will have advanced each other just from this experience.
Thank you very much. So you can start your presentation. And before this, I want to say something about questions of our audience.
Sure.
You can ask your questions in chat box, and at the end of the presentation, I will ask your questions and my questions. So that's it.
Okay. So have you enabled my sharing?
As it works? Now?
Now, yes.
Okay, thank you very much.
Okay, and let me fix the size. Is that showing well to you?
Yes, yes, Prof.
Okay. So, oh, and I would like to note that I wore this IEEE Day color jacket.
Oh, yeah, you look great,
So,
yeah.
yes. So I like to be fully integrated. So evolving cyber systems in avionics is my topic today. And I had some background prepared, and I'll mention a little bit of it, but you covered a bit of it in my in the questions that you gave me in the opening round. And so part of the motivation for this is that I'm currently chair of the Cybersecurity Technical Panel for a society, IEEE Aerospace and Electronic Systems Society. And there's a lot, even though I'm chair of the Cybersecurity Technical Panel, there is an overlap and energy with the Avionics Systems Technical Panel, and I'll give you a little bit on those at the beginning. And so my own personal technical journey started fundamentally in computer. And that was from the time, you know, even in high school, which at the time, I don't like to admit my age, but at the time it was unusual to have computer in high school. And then my senior project as an undergraduate, and then as a graduate student at Caltech, I was concerned with, I wasn't sure what I wanted to do research in, but I knew I wanted it to be computer and communication related. And eventually I ended up inventing at the time, the largest, fastest computer arithmetic divider in the world for an application in cryptography. That was what I was working on at the time. And so that was my first, and so my first conferences and my first publication was a Computer Society publication, a Computer Society conference. And over the years, I became a faculty member and I worked at these companies, and I was doing different activities that I don't want to take away all the time to talk about it. But I happen to live in San Diego, and my personal story is very much a California story. But I discovered my connection, that I could collaborate and connect, and that's one of the things that drives me with so many more people and have such a wider world through my activities. And so for me personally, I really enjoy bringing people and activities together so that the whole can become greater than the sum of the parts. And I really have the opposite of one of my favorite classes in graduate school was game theory. So it's linear programming and game theory. And, you know, a very brilliant person teaching this class. And I really loved it, and it taught me a lot. And there's a term that people use that's quite meaningful called the zero-sum game. And I appreciate, I think it's a higher level of knowledge to understand when you have a zero-sum game and when you can change the game and make the whole greater than the sum of the parts, so that it's not I win and somebody loses. It's we can both win and we can both move forward. So I enjoy bringing people and activities together, and I like to seek out meaningful progress on high level challenges. So in terms of these cyber and avionics panels that I'm talking about, the cybersecurity panel that I chair, I'm one moment. The cybersecurity panel focuses on cyber technical interests that are most relevant to complex systems for space, air, ocean, and ground environments. And so these technical areas, so when I say cybersecurity, I don't mean the more general traditional cybersecurity with the traditional hackers that people are concerned with, although I do care about them. But I'm considering issues like threats to the GPS system, information security of very complex systems, and cyber-related vulnerabilities of these cyber physical systems. And then on the avionics side, which in my history, I really wasn't very knowledgeable about avionics, but I was invited to be involved with something, and it just got bigger and bigger. And so now I am an avionics person. And so the avionics system panel is systems for aircraft system, and the word avionics comes from aviation electronics. So this includes communications, command and control, navigation, surveillance, manned and unmanned air traffic management, and space systems. And so for this presentation that I'm giving you today, I particularly want to point out that I would say at least half, if not more than half, of my slides that I'll share with you were contributed by my good friends on the avionics systems panel. So we got together and shared a tutorial for 3 hours about a week ago. And so all of these gentlemen, and I am the one woman contributor to the panel, but it wasn't a women in engineering issue, but I'm very glad that I was participating. And so they are very, I admire them very much and appreciate having them as colleagues and their marvelous contributions to this. And so we gave it at this Digital Avionics Systems Conference, which is coming to Europe next year and will be in Barcelona. And so getting an idea of the space, we have the global airport transport challenges. So if you're looking ahead 25 years from now or more, the traffic, air traffic in general is expected to be increased by a factor of 4. The aviation induced global warming increased by 10%. Driving interest, a large number, or let's say a high degree of interest in advances in aviation that might better address that, such as electrification. And the Asia Pacific share of the global air traffic could increase to 1/2 of the traffic. And we have an evolving, what we call an ecosystem. And so probably even if you are completely like if when I said avionics and what it meant to you, and it said to you, and you were like, oh, that's completely, I've never heard even the word avionics before. Probably you are, and even then you're aware of a lot of these systems that are related to that. And so on the horizontal axis, what I'm showing you here is there's international treaties, and here it says Department of Transportation, FAA, which is, essentially government regulation. So on the European side, you have EASA, for example, and there has to be a global cooperation on all these policies because people are not just flying within one country. We have air traffic, and there has to be management of this in the airspace, automation, and drones, whether we're ready for them or not, have emerged. The communication channels, the navigation channels, and the surveillance, which I don't know why I'm having trouble pronouncing that one today. So navigation for me is a topic that technically I have a lot more ties to than the broader avionics. And so if you were to go look at what papers has she done lately, a great deal of my papers are about navigation, and I do a distinguished lecture that I flatter myself is quite interesting on the topic of navigation and looking at GPS in particular, and I'll talk a little bit about that. Now on the vertical axis, you can look at it in terms of basically how high up are these things, and so our regulation is at these different levels. And so some of the really interesting work, or this is just my opinion right now, the real interesting work is the low Earth orbit and the Starlink's type communication networks, as opposed to the
It looks like Carmen Fuentes.
as opposed to the FL, the lower aircraft or more traditional aircraft. So in terms of the airspace evolutions, we have the regulated airspace that is the typical commercial and non-commercial aviation, and we have the space, which is the Starlinks and higher that I'm mentioning, and the subject of a great number of movies. And then we have this sort of wild west of the unregulated, where everybody is going in between and many things are happening, and it's becoming an issue, shall we say, and it's an issue of interest. And so that's what's happening. Now, in terms of an avionics framework for cyber, here is a different look, and this is with the thoughts of how are we going to advance. And so one way to look at it is the advances in sort of the fundamental tasks of communication, navigation, and surveillance, which is very commonly abbreviated as CNS. I tried to go through the slides and get rid of many of the there's a tendency in each technical world to overuse acronyms, and so I did try, but it's a battle that is hard to win. And so CNS, so communication, navigation, surveillance. So we have an evolution going on there in terms of a certification framework, and that's, I have a slide later to talk about this change and sort of this ethos, if you will, and I should be careful of using the word ethos. So a paradigm that is long established and highly regarded in the industry, and by industry I include government and constituents, that things need to be certified. And so whenever you have certification, somebody needs to do the certification, and you have to have a meaningful thing to certify. And this whole certification mindset, as you'll see on a later slide, is stemming from late 70s era views of computer systems. And so we're having a real struggle. So if you talk to somebody from Silicon Valley or the sort of your more traditional disruptive technology people, there's papers on sort of embracing this paradigm of the disruptive technology, and you really want to be highly disruptive in your technology. For those in aviation and aerospace, this is something that is counter to everything that they value and have been taught about the regard for safety and the real risk assessment. It's been very interesting to see, as we've experienced the pandemic, for example, how the aviation culture has always recognized that the risks exist. You have many, many risks, and it's not avoidable to have risk, and it's not possible to be safe. It's only possible to have a certification that you're this safe. And it impacts how changes are made and how people innovate. And so it's very interesting to contrast the aviation milestones or innovations with, say, the automobile milestones and innovations. And so they are, you could really argue that they are closely allied industries, but they have a very different philosophy about their responsibility and their ethical responsibilities as they are being disruptive or perhaps being disruptive. So we have this integration and security issues, and this has been a major focus of my cyber panel. And so on the one hand of avionics, you want to have fault tolerant design. And so, you know, if the engine goes out, you still want to be able to land. But the most innovative and bleeding edge advances are not in the mechanics. It's a little bit in the power, but not in the mechanics. And then we have what are cyber physical systems at this point that are combining the avionics with so the avionics, if you're talking about on board and on the aircraft, whether it's a drone or craft, and the air traffic management of that craft and then from the ground. And so then we have multi-domain avionics. So you have an integration. So you have all these different classes of craft and purposes of them. And they're using, you know, there is only one universe that they're in. And you care a great deal about their interference with or potential risk to each other. And then automation and autonomy. And so I think it's been really obvious to people, even completely outside of the field, how automation and particularly UAS in the more general sense, and the advances going on there, how that's changing. It's changing not just how you interact with, say, airspace, but it's changing the world and the risks and the problems that you need to solve. So here's some challenges and opportunities. So we want to enhance safety, efficiency, and sustainability. And so I think it's important to remember that for the aerospace types, the safety is the first word that they would come up with when they're discussing the importance of it. And so some research and innovation areas for students or interested people. So next generation ATM communications. So that's ATM is air traffic management communications and navigation and surveillance. The avionics system. So CNS plus A, they an acronym. Now, the next generation sounds, and in fact, it was one of my campaigns. So I could talk about my campaign now because the election ended yesterday. We don't know the results yet, but the election ended yesterday. So I'm allowed to talk about my campaign more publicly. So in my campaign, I have as a priority to inspire and engage the next generation. And what's interesting to me is when you say next generation in aviation, they mean the next generation essentially of navigation and air traffic management. And this next generation is not, and if it ever was, it isn't a good use of terminology, or it's a misleading terminology, because it's been, it might have been next generation when it was originally conceived, but it's been limping along at literally decades at this point. And so, but we still have the term next generation. And but it's next generation based on now decades old technology. But when an aviation person says next generation, this is what they mean. So the UAS, or also known as drones, access to all classes of airspace. And so that is a challenge to have. You have to be able to trust the autonomous vehicles. Improved efficiency and capacity of airports. So one of my earlier slides said how much the traffic is growing. And so whether you're talking about air, sea, land, the capacity, these pathways by whatever means of travel are, and the locations where you can park are fundamentally limited and congested, and yet the demand is increasing. So how many extra approaches to an airport do you think they're going to invent for a long established airport? It's a difficult, this is a difficult problem. As I mentioned, I live in San Diego, and San Diego, our airport is named after Lindbergh, who did much of his early work on flying on the planes here in San Diego. We had a project that lasted over a decade trying to come up with a new airport, and it ended in failure. So for these cities that are long established, such as in Turkey, such as anywhere, it's a very difficult, almost insurmountable problem to come up with. We're going to have a new airport, so there's a great deal of work being done on how can we have the next generation, a new version of an airport that works just for different things than the current commercial airspace works for. And then solutions for enhanced safety and security. And again, notice that there's always this tendency to use safety as the first word being used. And when you look at the work being done in other spaces, they do mention safety, but they almost never mention it first. So some of the interests that I've had in particular, this is sort of translating the avionics into the cyber awareness issue. So looking at the networks that are involved, so meaning generally the communication networks. So we have various fixed and wireless ground and air networks that enable the information to get between the aircraft, the ground, and space. And so certainly examples include the air traffic management and IP addresses involved in that. We have onboard, so as I mentioned earlier, avionics is really the coming together of aviation and electronics. And so together that word is avionics. And so the electronics that are on board are subject to internal and external performance requirements against size, weight, power, battery powers, the sensors that are supporting the engine control and diagnostics, software. So we have modern systems that are operating with large data control, runtime operations, sophisticated methods of efficiency, including in particular, like yet another acronym, but the integrated modular avionics. And then where you see much more ability to do interesting things in the shorter term is on the analytics. And so we are recording all this data, and then you can run your computational intelligence solutions and just you can consider things, you can at least analyze them, even if you can't implement them. So availability, confidence, and processing of systems determined by various standards, and particularly GPS and ADS-B. And the ADS-B is about, it has to do with air traffic. And it's basically that it's important. You have a really big security problem in that the modern navigation is relying almost entirely on GPS, GNSS, global navigation satellite sets. And so GPS and its variants are not perfect. You're relying on, there's in the case of the GPS system, which has the most satellites that's working at that level, you have, although there's a Chinese one that has, I guess, more satellites, but it's focused on China. And GLONASS has some, and then the Galileo for Europe. But these satellite signals are tiny. They're really tiny from a power point of view. So the effect of that, so when you have like 10 to the minus 15th watts, it's really easy to even accidentally jam. So let alone if you have, so let's say hostile, those who are hostile to that solution. So you have, there's a great deal of consideration. So you put in the hands, or relying entirely on navigation satellite signals that are very tiny, and that from a security point of view, the whole point of traffic management is for people to know where you are so that they don't hit you. And so the cybersecurity is, you don't want to have the information hidden, but you do want it to be reliable. So this is let's just say it's a problem. So communication is a coordination of the signals that are transferred. For air operations, we have space and air pathways, performance-based navigation signals for coordinating flight. So with that, the global sort of traffic management navigation, and so there's some of the advances are in performance-based navigation, so that you're planning much more efficient, faster routes because of the planning and the coordination. And then on the data itself, on physical networks, communication pathways, data and protocols need to provide that. So system-wide information management. And so this is looking specifically at avionics. In the case of something like Starlink or those low Earth orbit satellite constellations, the whole purpose of those systems is data rather than the movement of the craft. And so, yes, there's some satellites moving, but the purpose is really the communication that happens. And so there's some obvious vulnerabilities that occur. When you're looking at traffic management, we have some key challenges. So the air traffic, so ATC is air traffic control. So the conventional method of air traffic control is one that perhaps you've seen in the movies, and that one is still largely in place. And so that one really has no room in it for drones to be part of the traffic. And yet, drones are clearly part of the traffic. So I was at a larger retail outlet here in San Diego about 2 weeks ago, and I bought a drone for $47, and a much more higher performance drone than I purchased for a few $100s a few years ago. And so, but the fact this large retail outlet is selling rather high performance drones for $47 to how many hundreds or thousands of people. So, but the air traffic control paradigm says that there is a human in the air traffic control tower and that is taking care of all this control. And so the current paradigm says we don't need to worry about drones at all. And so they just need, they're just directed to not be in the way and not be in many places. This is not a long-term solution, particularly as more and more and more of them exist, and if they're being used for anything beyond casual recreational use. So the UTM is basically management of UAS or drones. And so the drones are not being flown. Right now, all the regulation in place, assuming that they're allowed, presumes that you have a line of sight on that vehicle at all times. And we know that that's not true. We also know that the management of it would require, cannot meaningfully require human awareness of at every stage of every drone by a central authority. That would be, I don't think it's a meaningful rule to say that you have at this point. So if you were to have, so whatever task, so when we say a UTM operator, so who is controlling this traffic management and whatever they're supposed to do, it has not even, there's a huge challenge in just defining the challenge. So urban air mobility or advanced air mobility is it's a look for major goal. And you see in this picture the term vertiport that's being used rather than an airport, which is the more traditional airport. And so we have safe automated air transportation is the goal. And so to have an ability to have your own regional system and to have a system that's effective in an urban environment would require this trusted autonomy, and so an ability to trust the autonomy and highly automated human in the loop operations. And so humans are very much part of the loop for manned aircraft. They bring about how do you decide who is responsible, and sort of regardless of where you live or what industry you're in, it's very easy to observe the effect of having distributed responsibility. And so when you have responsibilities that are not clear, in the long run, then you have no one with responsibility. And so this is a major issue for the future. So one of the major advances is in four-dimensional trajectories. So the fourth dimension being time. And so you have innovative support systems that are looking ahead to all this interaction. Another application example is for the computational example is the adaptive control. So the ability to respond to the situation. And I think a very accessible analogy is the self-driving cars, that you as you know, you can't just plan the car's route and how it will drive at each point along the journey. You have to have an ability to respond to the changing situation. And so this is one of those opportunities for more, this unpredictable element in flight control is an opportunity and a challenge. The separation assurance and collision avoidance, that's the whole point of, or one of the major points, let's say, of it's the first point of safety on traffic management. And so you don't want people to die, you don't want property to be lost, and so you don't want collisions and the harm that comes from collisions. And so the way you avoid collisions is by ensuring that you have the right amount of separation. And so there's all kinds of advanced technical techniques that are used in order to assure that your autonomous flight is maintaining that separation and avoiding those collisions. And so this is a major technical, let's just say, challenge and opportunity. Similarly, in the space domain, we have this same issue. So whether we're looking at the lower level or the higher level. And so we have a whole subject of problems that this whole collision avoidance and so sense and avoid. And this is the common terminology, is sense to avoid. And so there's, how are you going to sense? Like, how are you going to sense, or do you have your situational awareness? And depending upon whether you have, so cooperative sensing is that you're working together to make sure that you don't hit each other. But non-cooperative, you really can't count on everything you need to know being cooperative, or some very negative consequences could ensue. We also have conflict detection. So we have a basic pilot alert, 3D prediction, partial prediction. And you see that if you have a newer vehicle with collision avoidance. So basic, remotely operated, and then completely autonomous. And then how is the cyber physical system going to be for that? At another level, particularly space systems. So where I've been asked to do some work that's getting a lot of attention lately, I put it in blue, is the constellation one. So there's all kinds of ways that we interact with space currently, and you hear about space junk and all those things in space. And so you have what are essentially satellites at different levels and orbits. And the one that's truly a constellation, so you have GPS is a constellation, and it's a constellation at medium Earth orbit. So are the other global navigation satellites. But we also have Starlink, and Starlink is unique in its success. And this slide says 900 plus, but I think the last time I looked at it, it was about, I'm going to say 1600, but I could be wrong. I last did a talk on it in January. But certainly you've been hearing about it. And so there's a huge contrast in this constellation approach. So when you have hundreds that are part of the constellation that are circling the Earth very quickly, when you have versus the navigation satellites that are more like dozens, and the cost is in the hundreds of billions to, I think I want to say the 100, yeah, it's certainly in the billions to launch one satellite. And then the one satellite, if you're lucky and it launches, it's in checkout for about a year. Whereas and there's many agencies and people that are involved all along the way, getting that one new satellite up and interchanging it with a network that's about 30. Whereas the Starlink is, okay, every month we'll send up another 50, another 70. And so that means that each one is less, it's not vital, that you could lose 50 and things still need to work. But the system then needs to be a much more dynamic constellation. So there's some very interesting problems that one could consider, and if one's interested in this. And so what about artificial intelligence and all this? So all these problems are pretty advanced, and artificial intelligence is one way to do that, to solve these problems. So we could look to be more integrated and more interoperable by using AI as kind of an overseer. We have UAS, again, drones, access to all classes of airspace. If we have trust, if the AI could give us trusted autonomy, which is our goal. We have improved efficiency and capacity of airports and spaceports, multi-mode. We have solutions for enhanced safety and security, and that's been a focus of my panel. And this is completely, this has nothing to do with aviation, but this is actually the EASA, which is the European Space Agency, Air and Space Agency. This is their roadmap, and this is stolen from their document that they posted. So not really, but from borrowed with attribution from their document. And so here you have the global world of artificial intelligence, and within that world you have machine learning, and then that's learning from these large amounts of data and on our understanding of the system. And then we have deep learning, which is a subset of the machine learning. And the AI roadmap, which first came out in 2020, and then in 2021 they updated it, was considering supervised, unsupervised, and reinforcement machine learning. And then you have these different applications. Now, this sounds wonderful, and I'm all for it. But there's some issues or challenges with, let's put it as challenges. So an AI technique, so machine learning, we have an AI technique that's teaching computers to learn from experience. So machine learning algorithms use computational methods to learn information from the data, and without relying on a predetermined equation as a model. And in fact, really what you're looking for is you're essentially looking to find your own equation from the model. So they're improving your performance as the number of samples available increases, and deep learning is a particularly specialized form of that. And so we have supervised learning and we have unsupervised learning. And so almost all the work I do is on unsupervised learning, but supervised learning I think is more interesting to some people. And the machine learning techniques, you have reasoning systems and you have learning systems, and certainly they can overlap. And so I like this slide as an introduction, and I want to credit to Ahmad Al-Nagar, Taxonomy of AI. And so here's all these different, I guess, cool words to use. And so if you have, so fuzzy logic control, expert systems, I think if you wanted to, you could combine almost all these things together. And so those of you that are interested in like more and more and more publications, so you can take one thing and add in something else. And so a great deal of my early papers, say from 10 years ago, were on fuzzy logic control systems, and arguably expert systems. And so it says programmed, but to me, I was over on the unsupervised learning for the fuzzy logic control system. So we have this taxonomy, but there's certainly a lot of interaction depending on what you're trying to do with it. So navigation, for example, is it's like I find navigation to be an interesting problem, and it's one where you're getting a lot of data, but you don't have to update your data as the way you need to if you're trying to send video. And because the navigation is about where you are and how fast you're going and what direction you're heading. Whereas the video, each fraction of a second, you're trying to send megabits of information. And so it's a very different problem, and you can do things in real time with navigation that you can't do with some other things, even image-based navigation. And so there's a tutorial that my colleague that I listed on this as a co-author, Eric Blasch, he's with the Air Force Research Lab. And so he has tutorials that he gives on these whole topics. And so you could also do artificial intelligence in the sense and avoid, and particularly for visual sensing. So visual sensing is very widely used, or anytime when people are explaining that their work is relying on image processing, there's a lot to be done in sort of autonomous vehicles with visual sensing and identifying. So there's some interesting work there in finding things. There's the work that's been done very well is focused, so like on vehicles, like following lines and finding the lanes. That's something that is, I guess, a good problem for visual sensing. Identifying numbers on license plates is a good problem for visual sensing. A good opportunity that we're still working on is visual navigation, where you're doing more than just following the lines. And so we have supervised learning. I want to finish up soon. We have unsupervised learning, and we have reinforcement learning. And you also could have sort of anti-reinforcement learning, which is a variation on reinforcement learning. And so for avionics systems in general, some applications of AI, so this advanced air mobility, which is variations on the air traffic control, space and domain awareness, some practical examples, autonomous separation assurance, so making sure to avoid that collision, the aircraft health and mission management, the vision-based navigation and landing, decision support for the traffic management, and distributed space systems such as the constellations on Starlink. And EASA, which I put in because this is for computer Turkey. So aircraft design and operation has been identified, aircraft production and maintenance, air traffic management, drones, urban air mobility, safety risk management, cybersecurity, and environment. But there's a large however that's coming. So in general for avionics, all these cool methods together, you can have contextual reasoning, statistical learning, and handcrafted knowledge, and it's waving together with these overlaps that you can do many interesting things in avionics. The higher level cognitive reasoning, where traditionally we have the human in the loop, there is a great deal of thought and work, and there's even been some advances that I saw just a couple weeks ago of some industries at the conference showing off some pretty amazing autonomous AI-based happenings. So one of them, Cirrus was showing off and they have personal aviation. So they were showing off if you had this small aircraft and there was some kind of an emergency and the pilot was gone, or unavailable. Let's say you had an unavailable pilot, that you could hit a button and this small plane would navigate itself to an airport and land completely on its own. So that is happening today, but there's a however coming. And another example was another company, and the company, you can find it. So they are handling deliveries for some small percentage of one of the major parcel deliveries. And so they have human piloted flights, but they are essentially not human piloted flights. So they are observing all laws required for human piloted flights, but the human pilots don't need to do anything. And so they're just flying on the plane for almost the entire flight. And so that shows an ability to do a great deal. So this autonomy certainly is in use and requiring, so the traditional filtering, estimation, analysis, and I would say I do a lot of AI applied to the traditional filtering and analysis. And so other people would, as in this slide, separate them and say that you looking at the AI methods outside of the traditional, whereas I'm kind of looking to combine them in with the traditional. And you have trusted AI, ethical principles, and data sharing. All these three things are necessary. The ethical principles are what bring us together as a profession, and you really can't advance without them. It might seem like they can be an afterthought, but they really can't be. Your fundamental movement forward, advances technically rely upon that, and so you can't trust without knowing what you mean by ethics. And you also have to have data sharing, and so there's certainly a major cyber problem in with regard to those getting to that goal on these problems. So I want to finish up. So there's the big however. So there's some big challenges. So a core premise is that AI is learning and adapting its behavior to achieve an optimum outcome. So the AI response for a given set of expectations in the given environment is not necessarily the same. It's not deterministic response. So you run, and so very often when people are doing research, they run runs over and over again and see what happens this percent of the time or that percent of the time. The aviation systems, the regulator expectation, which derives from decades and decades of basically a century of tradition, is that for every scenario, and certainly from the late 70s onward, that for every scenario we have a complete prediction, an expected system response. And so AI does not play well with that standard. So an approach could be acceptable error tolerance, but right now that approach is not there. So we have data set availability. So we have all kinds of things that are helping us move forward, but that challenge on certification is a very significant one. And then on the cyber in particular, again, I showed you this earlier. So looking at the cyber awareness for avionics in the light of these topics, particularly on AI, you can see there's a role for each one. And looking at, so STRIDE is an abbreviation, one abbreviation that of Microsoft. And I would like to give credit to the right author, but Microsoft only shows it as, Microsoft Magazine uncredited. So whoever did it, I'm happy to give you credit. So the STRIDE, and you can see the acronym on the side for all these variations on vulnerabilities. And then you could apply this to the cyber physical systems involved here of the avionics and air traffic management for the future. And so all of these, there's cyber vulnerabilities across. And then finally, the key standards. We have the, these are, when you talk to somebody in the industry that's, let's say an experienced professional in the industry, they will tell you that I have experience, and they'll list these numbers as their competence and their expertise. All of these, you can see some of this is from the late 70s. Some of these are from 22 years ago. And they're considering, you're looking at the in-flight entertainment system and how you can access things and what you can get to from the avionics bay of the aircraft. And so you have the Radio Technical Commission for Avionics on airworthiness is about certifying that you know exactly what will happen. And so these key standards don't work well with AI, but clearly AI is needed to move into the future. So there is a working group, and I wrote to my dear friend James Gill yesterday, since I was going to give my talk for you today. And I was like, James Gill, and he happens to be the vice chair of 802 for IEEE. Like, what is going on here? Why is IEEE taking the backseat to SAE on these major standards? And so he said he'll get back to me on that, but he wanted to point out that the RTCA ones do have heavy IEEE involvement. So his is Working Group 34. And so they are looking to come up with the standards that will allow this to move forward. So the major issue here is that we're at phase 1, which is coming up, which is still defining the problem, which I like to tell my students is often the hardest part of the problem. And so I'll point to some references as I finish up, and that I'm happy to share with you, and just send me a note and I will write these back to you. And I did again want to give credit to my co-authors on this for my shameless use of some of their slides. Thank you.
So thank you for your presentation. It was great. And I have some questions about also your studies and presentation. I had an opportunity to read your article, which is displayed in 2019, called Cyber Awareness Trends in Avionics.
Ah, yes.
And you mentioned about firmware and network attacks in cyber system in avionics. And I have a question about it. What precautions can aerospace companies take for these attacks?
So the question is, so what precautions can aerospace companies take for what about the software?
Yeah. These attacks, yeah.
So it's actually rather difficult. So it's a difficult problem. So looking at, sorry, to smooth to go forward. Okay. So these standards are currently in use in commercial aircraft. And so the 178C is what people rely on, but this is completely, so for more advanced software, there hasn't been, it's been very limited. Everything, the emphasis has been on certification, which means that everything's completely predictive. There was an interesting paper that I saw done a couple weeks ago, where they were considering the how to maintain the security of the software. But it is like the need to be fully certified. It's a major challenge. I would agree.
Okay, thank you very much. And we have a question from our audience, Alperakius. Do you think the malicious usage of drones pose a risk to aviation safety? And how should the risks be mitigated by drone manufacturers and national authorities?
So yeah, so this question, Amir, is about, so they're asking how you mitigate the risk and whether we're concerned with malicious act, and you have to be. And so, like, you don't need to be concerned when it's a very rare thing. So when there is, you know, so I'm not concerned. I'm not a, I'm a mother, and I have my husband, I have 3 children, and I do not cook. And so if once every year I make a cake, I'm not so worried what'll happen with that cake because it's only like once a year I might make a cake. But as we get, as I mentioned in my talk, like when you have drones that I can buy for $47.74 at my local Costco, so that means that thousands of people have drones. And so how long, so there's malice, even like you don't even have to have malice is one problem. So some of my work I've done in the past is on GPS vulnerabilities. And so people don't realize, so GPS is the backbone, GPS and its global counterparts is the backbone of navigation of the air systems, and it's the backbone of navigation of almost everything else too. And so with these tiny signals, all you have to do is jam a tiny signal. It's like the difficulty of jamming these signals. It's not difficult technically. It's a tiny signal. You can swamp out a tiny signal with no effort. So my city is known for being, and I get the impression, look, I'm doing some work that has to do with Turkey lately, and I had no idea how maritime oriented, naval, the oceans going that Turkey was, until I'm now realizing this in my other life. And San Diego is very much a coastal environment. So the US Navy was out doing a training exercise, as they often do. And this was more than a decade ago. They didn't try to do it. They accidentally took out all of the GPS for the entire coast and in the coastal area. So what did that knock out? Accidentally, not even maliciously. So you knocked out air traffic control, all the bank machines, the traffic lights, so many things, and completely without malice. So let alone if you have to be concerned about malice. So no question.
Okay, thank you very much. And my last question is, what advice would you give to students and engineers who want to improve themselves in avionics software?
Oh, so that is an interesting question. So I would say that I would take a step back, and I think it's too specific to improve yourself in avionics software. I think that the solution is to improve yourself in cyber physical systems. And then that you will find by looking to improve yourself in cyber physical systems, that you have not only fulfilled like the greater goals of the Computer Society Turkey, but you have also you've hit where the real need is, and there's a great deal of demand for that expertise. And so there is, in the last, I would say, I'm going to say 6 years, it's hard for me to track time, but so in the last 6 years, what I've seen is many students looking to online videos and open coursework to learn new things. And this, and there's nothing wrong with that. And I think I love to learn, so I like the idea of learning. But what you really want, this is the ultimate collaboration. And so you want to work with people that are really doing something, not just learn in the abstract what they can share openly, but learn as a contributor. And so, and where they need contributors is where both the cyber and the physical. So not the quick, I'll pick up a certification in something and then they'll hire me, even though I don't really know very much. But so I always tell my students, you want to be looking to bring something to the table. So what are you bringing? And so it's not how, like, developing a little expertise. It's more like appreciation of the cyber physical. So actually, try to do something in that and look for people that, and so I think I've seen many are inspired by doing that. And so there's a lot of opportunities.
Okay, so my question is finished, but there's another question from our audience. And if it's proper for you, can I ask the question?
Sure.
Okay, so can integrating data from multiple platforms be used to reduce the effects of electronic warfare on military aircrafts?
Oh, well, I think the answer has to be yes, but I would say that that the best thing that you could do to, if that is an interesting question for you, then I would point people to that AESS, which is not computer. I'm a member of computer, but I'm a distinguished lecturer for AESS. And so I have some colleagues that want to be invited to give a short course for you on electronic warfare. And so that's what you should do instead of, so if I had to give you a nice lecture on electronic warfare, what I would truthfully do is I have a few friends of mine that I could point you to, and I would ask them to come, and so it's a great chapter opportunity to arrange a short course, and so you can everybody wins with that.
Okay. It will be perfect for us, and we're so appreciated to welcome you again, and thank you very much. It's a pleasure to meet you. Thank you very much.
Thank you, and happy IEEE Day.
Thank you.